Thank you very much for the intro. And ladies and gentlemen, let me start with a very simple question. Have you ever heard the phrase that you can count everything in the world, but it doesn't yet necessarily mean anything? Quantification of semantics, quantification of unstructured text is precisely what we do at Sustainalytics a lot. And if you think about the question I posed, counting everything, but still thinking whether it would mean anything, an example that crossed my mind is that there are two groups of people counting stars. One is known as astronomers, the other is known as astrologists. What makes the difference in how you count, what your approach and what your methodology is. In the knowledge acquisition, knowledge management industry, in the sustainability research and ratings industry in particular that we represent, one archetypical job that we do every day is quantification of meaning in the text. We as a company go through countless pieces of text and we look into them, and our analysts assign numerical values to those texts. And these numerical values, they can be indicator values, they can be ratings, are used in the end of the day by our clients, responsible investors, for their decision making. And that's the challenge that we've been facing for some time, probably from the beginning of our company, we'll be facing for some time. The challenge is how to make this quantification even more meaningful and even more reliable. Today we'll be talking about our recent project in this direction. I'm Arik, Brutian, I'm the head of the digital innovation team. My colleagues Mihai, Ilie, and Andrei Hera are the senior machine learning engineers and the men who really did the job on the project that we're going to be presenting today. What we'll do today, we'll go through, I'll briefly present sustainability research and ratings industry. I'll talk about Sustainalytics, and I'll outline the challenge that we've solved from the business viewpoint. And then Mihai and Andrei will take over, and they will talk about the solution and about the lessons we learned while implementing our solution. Let me briefly start with an intro into sustainability and Sustainalytics. Sustainalytics has been around for about 30 years, and we operate based on the imperative that it's important for the global economy to become even more just and sustainable. And the last year with COVID has shown how deeply interlinked all the countries, all the economies of the world are, and how important it is to make sure that whatever happens, the level of justice and the potential for sustainable development is preserved for our and for the future generations. Our mission as a company is to provide our clients, asset owners, asset managers, and the corporates with informed decision-making points that would lead through their decisions to this more sustainable and more just economy. Last year, we've become part of Morningstar, one of the leading financial information providers. Before that, for 27 years, Sustainalytics had been probably one of the biggest and one of the first sustainability research and rating firms in the world. We have Sustainalytics only about 900 professional staff all over the world, half of them engaged in research. We're present in many locations you can see here on the map. We have more than 700 clients representing asset owners, asset managers, and also corporates. All the important players in the economic life come to us for our advice, for our guidance, for our ratings on sustainability or otherwise environmental, social, and governance, ESG performance of either the firms they hold, companies they hold, or their own. The type of products and services we provide range all across the board of sustainability offering. They start from ratings, numerical ratings, from research in compliance or screening type of research. We very often look and regularly look into how different companies are engaged into practices that might be of concern for their investors. We also assign ESG or sustainability ratings, and we conduct research on country level. We look into corporate governance. Our research and our ratings are used also for strategy development. We provide and we develop also indices all across the board for sustainability practices. We are a one-stop shop for investors and for corporates. The challenge that we are going to be addressing today is quite simple. I'll use the information value chain pyramid just to outline that. I would say that every knowledge firm, and we for sure, start with acquiring facts, acquiring observations and discourses, normalizing them, bringing them into the form of normalized data. And from normalized data, what happens is that our researchers assign scores to data. This is where this transition from this bottom part of the pyramid to the mid part is where quantification of semantics, precisely the topic we're going to be talking about today, happens. Later, based on this quantified information, we develop ratings, reports, company profiles that become input for our clients' decision making. And this transition from data into information, being important per se in general in systems theory and cybernetics, is key also for our business. Let me outline the challenge with an example. When we talk about quantification, what we talk about is looking into a text, as I've said, and assigning a score. But what does that look like in the real world? Our archetypical case looks like as follows. Our analysts look into the text and assign very often a binary value. We'll call it a tick box. So suppose there are senior management, there is an environmental policy approved by senior management of a company, and there is a proof in the company reporting about that. Then we will tick the box approved. But suppose there is no commitment to consult to stakeholders. We don't find any evidence of that, or we find no evidence of the existence of this commitment, evidence of non-existence, sorry. Then this tick box is not assigned. So we start with binary judgments. Then binary judgments, a family of binary judgments meaningfully bound together, becomes what we call an indicator. Based on the amount of tick boxes and weight of tick boxes selected, so weight of these binary states, we have a numerical value assigned to an indicator that could be called environmental policy or scope of social supplier standards, for example. Those indicators together become visible for our clients, and they also become building blocks for our ratings. And that's precisely where we use a lot of manpower and a lot of time and effort, our analysts especially, to correctly and accurately assign those tick boxes. And from a certain point, we started to think how we could be helping our analysts to automate this process to the biggest extent possible, so that analysts don't spend as much time on doing that work manually as they could be by assuring the quality, by going through the judgments, and by looking into the corner cases, doing the more meaningful and more complex job. That is the challenge that we've outlined. And from this point onward, I'll hand it over to Mihai and Andrei to talk about the solution.
Can you share the screen, please, Andrei?
Yes. It should be visible right now.
Okay. I requested control.
Oh, okay, perfect. Yeah, here it is. You're on.
Okay, so why it is not working?
Okay, let me help you with that. So
can you put on slide 10, please?
Yeah. Okay.
Okay. Automatization of repetitive tasks represents the future of work. Basically, it's transforming all the businesses by enabling humans to focus their attention on more creative and more demanding tasks. Most of the machine learning algorithms that we are using today in production were developed back in the 80s. So what has changed since then? The real breakouts that happen in machine learning and in deep learning is the fact that the computational power used to train the largest models has doubled every 4 months since 2012. Also, the data has become much more accessible and easier to crawl from large websites and store on huge data drives. But these algorithms need to be trained on labeled data. This is why labeling data is considered to be the engine that powers machine learning. Fortunately, in our company, we have human experts who are specialized on key domains, and they manually annotated our documents by extracting business-specific citations. They helped us by creating a citation annotation database. Here, a citation is composed from a chunk of text from the document, which the human expert annotates as being relevant to meet a certain business requirement and attaches a label to it. Note at this point, the citations are done at the document level, which means that we have to read the entire document in order to find the citations. And not all the information from the document is relevant for the citation itself. As you can see, in our final solution, we want to automatically filter all the irrelevant information from the documents. So we extracted all the paragraphs from the documents, and if one paragraph contains the citation, we consider the information from the paragraph as sufficient for the citation itself. As you can see, the dataset will contain paragraphs from the documents which have attached labels for specific requirements. Here, we define a label as being the indicator code plus a tick box ID, and both serves as identifiers for the citation. In order to obtain the dataset, we need a preprocessing pipeline. Our raw data is stored into a PDF. So we have to work on a process in which we have to extract from the PDF a structured text file. For this, we used a tool called Grobid. Grobid, which name stands for Generative of Biographical Data, is a tool that outputs an XML file for each PDF. It has advantages over other OCR techniques, such as it's easy to use, it outputs an XML file which we can extract paragraph from, and it's easy to parse. And this is the reason why we use it, and because it's much more faster than other OCR. It takes a couple of seconds to pre-process PDF compared with Tesseract, for example, which takes a couple of minutes. As you can see, we take the document and convert it into an XML file, parse the XML file, and extract the paragraphs. After that, we apply the name entity recognition on clean text for each paragraph to hash the named entities. By doing so, we observe that we increase the true positive rate and decrease the false positive rate when matching the paragraphs with the correct citation. On the NER paragraphs, we apply the term frequency inverse domain frequency models to convert a paragraph into bag of words feature vectors. We apply the same TF-IDF models on each citation from the database. To compare how much citation resembles the paragraph, we applied we measured the cosine similarity between their TF-IDF vector representation by applying dot product. We measured the cosine similarity with a specific threshold, and if it was greater than the threshold, we attached the label from the database to the paragraph and put it into the dataset. Otherwise, we put only the paragraph into the dataset with no label.
Okay, thanks, Mihai. So after we have the data set, so what Mihai told us and showed us how exactly we process the data and how we extract and compose our data set out of just pure citations and PDF documents. Now the challenge is to take this information and use it into a model, of course. The ideas or the constraints that we had in when building this project were due to the fact that our models needed to be scalable. So when we first started working on this project, we had to find texts for about 100 tick boxes, but we were expecting in the near future to reach a number of about 1,000 tick boxes. So the number of classes that we need to find information for just keeps on increasing as analysts gather and process more data. Now, another constraint for us was the fact that we needed this model and the solution to work fast. We're aiming to help our analysts, and by helping them, we need to develop tools that they will actually use. So if we generate and create an awesome model, but if it's slow, then people won't use it. So we needed it to be fast. That means we needed it to be fairly lightweight when it comes to processing times. And another constraint or another requirement for the project was the fact that we needed it to be easy to retrain. So if, for example, we have one class that behaves very well and another one that behaves very poorly when we try to extract information for that particular class, we might want to retrain the entire model, or not necessarily the entire model, but just to retrain the particular type of the model responsible for extracting information for that specific task. So in the next slide, I'll just walk you through how our processing system works. So we have the information that Mihai told us about. So we have the documents. They are being split into paragraphs, and then what we basically do is feed them through an encoder network. And afterwards, using this encoding, we just feed them to multiple feed-forward networks. In this case, the feed-forward networks are specific and trained just for a binary classification task, and they do not share any parameters amongst them. So we take a document, we process this using GrowBid. We have the document split into paragraphs, and then what we do here is just get one paragraph at a time. And we feed it, and we feed it to one of the two encoders. So we encode it using the universal sentence encoder by Google. And afterwards, when we get that encoding, we take the same paragraph, encode it using Latin semantic allocation. And what we do is just concatenate the results, and then we send the encoding vector to each particular feed-forward network to get a result. Bear in mind that these classifiers or the paragraphs, they can contain, or information in one paragraph could be relevant to multiple classes, or if we go back to the tick boxes, they can be relevant to multiple tick boxes. But for simplicity, we'll just take an example, and the classification example is as shown here. So we have that paragraph, and it's relevant for it contains information relevant for one particular tick box. Now, what we do for a company is you usually have multiple documents for a company. So we take all the documents for a company, and we process the information, and we run the information extractor as shown before, and we just process each individual paragraph. And at the end of this, we'll have a large list of paragraphs labeled as being relevant to a particular tick box. Now, when we have this information, we are at a crossroads here. So what do we do with this information? So we developed two approaches. One is the one we called an analyst assistant, where the paragraphs are forwarded to analysts, but they're not just forwarded to analysts. We do another processing step here. So in this stage, we want to rank the paragraphs as according to relevancy. So we don't want to give the analysts a huge list of paragraphs. So we want to give them a curated list, or let's call it a reordered list of relevant paragraphs, so as they can find the relevant information quicker. What we do here is we use the FACE ranking system. It's it comes from Facebook. It stands for Facebook AI Similarity Search. It's a wonderful library that we found about. We've researched about it and heard about it last year at NDR. Just a quick side note. And we've used it to rank the paragraphs being detected for particular tick boxes. What we do here is we get the paragraphs. We already have the encodings in the universal sentence encoding format. And on the other hand, as Mihai stated previously, we also have the citations being relevant text, relevant sentences, or probably paragraphs for particular tick boxes. And what we do here using the FACE system, we run multiple queries. So as each individual query will give a particular ranking. And using just a simple voting system, we decide on which are the most relevant paragraphs, and we just rearrange the paragraphs, and then these rearranged paragraphs are forwarded to the analysts. And our aim is to simplify the work for analysts. So ideally, and in our tests have shown that usually the relevant information is stored within the first paragraph. So if an analyst finds useful information in the first or the second paragraph, then he doesn't need to look into future paragraphs. So his work is basically done for finding the information for this particular tick box. Now, the other approach is an automated evaluator, where we take the decision automatically. So in the first example, our results were curated by humans. Now, in the other example, what we do here is just take the decision scores from the previous classifier, just take the maximum score. We're just interested in finding if at least one paragraph is relevant and contains useful information for a particular tick box. Then if that condition happens, then we're happy with the results. We consider the tick box to be ticked. So the binary result will be put to 1, and afterwards all these binary results will be sent to our Sustainalytics algorithms and methodologies, and the final scores will be computed. So each individual company will get its rating according to the tick boxes. Now, Mihai, you're up.
As a quick statistics, our data contains 150,000 citations, 3.5 million paragraphs, and over 200 classes. This means that we have an unbalanced data set. For this reason, we used a special metric to measure the performance of the classification models called the Matthew correlation coefficient. The Matthew correlation coefficient is a performance metric that is quite more complex than other correlation metrics such as precision, recall, F1 score, and accuracy. It is quite said that it is more reliable than all of them on unbalanced distributed datasets. We observed that in the numerator, it contains all the terms from the confusion matrix, such as true positive, true negative, false positive, and false negative. We should not worry about the denominator because it's just a normalization constant that is always positive. This points out that the result of the Matthew correlation coefficient will always be a value between -1 and 1. A high value, close to 1, means that both classes are predicted correctly, even if one class is overrepresented than the other. A low value, closer to 0, means that the classifier performs randomly. An even lower value, closer to -1, means that there is a total disagreement between the predicted values and the actual values. Following in our experiments, we played with versions of splitting the documents. When splitting the documents at sentence level, we found out there were too many sentences, so the precision of finding the relevant citation was low. When splitting at page level, the recall and precision were good, but there was too much irrelevant information in the page for one citation. Even when splitting into blocks of 500 tokens, there was too much information for the citation. We found out that the best splitting was done at paragraph level, as mentioned earlier.
going on with the models that we used, so coming from the ways we've split the data, of course, the information for choosing one particular type of text split was, in the end, it came down to the performance. And we've tried and experimented with all sorts of text splits. We tried and experimented with all sorts of methods. So we've just highlighted here a few more meaningful experiments. As we said earlier, one of the constraints was that we needed this model to be lightweight. Of course, like any NLP researcher, we've jumped towards the big models, so the BERT models with a lot of parameters, great performance. But due to the fact that we had so many classes, and due to the fact that, in essence, we had few true positives in our data set, we didn't get any outstanding results. So we tried classification using BERT. We tried just encoding using BERT and the large models, of course, all and multiple variations of BERT. But we didn't get any meaningful results. We've, on the other hand, we've switched and went towards the lightweight models. So TF-IDS with a simple machine learning model and XGBoost. And we've gotten different experiments here, but in the end, the performance wasn't that meaningful. So going further, we've tried different test splits, we've tried different encodings, and in the end, we've came to the conclusion that the most suitable result was achieved when we encoded when we split the text using the LSA, and then afterwards when we encoded using universal sentence encoders concatenated with LSA, and just feed the information forward towards small independent multi-layer perceptron. So using this simple yet not simplistic architecture, we've gotten very good performance. So for what we've planned to achieve, when we talk about the two splits or the two parts of the project, one being the analyst assistant, we've found that for most classes we achieve great recall. So we achieve the recall that we want. We always find the relevant information within the top 5 paragraphs. So we're very satisfied with this, because previously analysts used to either analysts used to search for relevant information by using some complicated regexes, which were fairly slow and gave a lot of false positives. Now we just give them 5 or 10, or they can even choose how many paragraphs they want, and then just the paragraphs are ranked according to relevancy, and they usually find the relevant information quicker this way. So it's both time saving, and it also we find what we're looking for. Now the other part of the project, the automated evaluator, we research a lot of companies. So we have a lot of companies, in the order of tens of thousands of companies being researched for different topics. So of course we want some capability to automate certain aspects for certain companies. And if we were to use this automated evaluator, we would get an average accuracy of around 90% with a recall of 70%. So we find about all the relevant information for the text that we want to process. Now, going to the lessons learned, we wanted something lightweight, but again, we've researched and we brought out the heavy guns, but in the situation, we've managed to achieve, at least for our tasks, we've managed to achieve great results using small models, but with the right encodings. So one of the interesting aspects and one of the most interesting things that we've researched during these months of working on this project was how we can leverage the power of encodings. So in certain situations, just by doing experiments and just by walking through and trying out different types of encodings, different architectures, different topologies, even for the same architecture, we were actually surprised to see that some simple encodings may offer awesome results. So just a quick example, the universal sentence encoder was actually capable of encoding and containing relevant information, even if we've encoded large batches of text. So I'm talking about 500 tokens, a token being a word. So even if we have large chunks of text, the universal sentence encoder was able to surprise us and actually conceive and have a meaningful way of encoding the information. And last but not least, it's something that sparked an interest for our team. So the interest from this project, and probably let's call it like a trampoline for different research topics, was a new idea or a new hunger, so to speak, to research aspects that come to encoding meaning. So it's a topic that I'm sure in the research community of encoding better ways of finding and encoding meaning in texts and getting meaning out of texts. So I am going to close my presentation here. So just feel free to contact us. I think we'll share the presentation with you, and we're open for questions. Thank you.
Thank you, Andrei, Mihai. So we still have, I suppose, a couple of minutes for questions that the audience might be having. I'd be glad to answer.
Our line, Arik, we're supposed to say thank you. Stole that away from us.
Giving it back to you.
Yeah, indeed, it was. Yeah, I found it a very cool presentation and interesting.
Thank you. Thank you.
Thank you.
And happy to know you're using face for this.
Yeah, it's true. We first found out about it at NDR last year. So, oh, this is interesting. Then a few months later, oh, we need to rank something. Okay, face it is. Let's see how it works. It's awesome.
And just curious, what tool are you using to track metrics?
So, like Mihai stated previously, no, it's for tracking metrics. We actually had something made in house, and it works pretty well. So just in-house logging system.
Right. So no ML flow yet.
Not yet.
Not yet.
But again, like in the previous year when we found about the face, now at this conference we've found more about ML flow. So maybe next year.
Well, looking forward to hearing how you've been developing the solution.
Awesome.
And if we have a couple of minutes, I see there are a few questions in the chat.
Yeah. One is, do you use graph neural networks?
We're laughing, Mihai.
No, not in this solution. No.
Not yet. We're laughing because we're at the moment we're actually researching a lot of topics related to graph neural networks. So,
but that's for one of the future conferences.
Next year.
Yeah. Yes. So we should build a to-do list for next year. Also, for what are you using the face from Facebook? There's another question.
Mm-hmm. So when we find relevant text for analysts, we usually, it depends on how we fine tune our models, but we might end up having more false positives. So the idea is just to present analysts with the most relevant information first. So what we basically do is semantically compare the text that were already highlighted by previous analysts for previous tasks with the text that we have right now. So and using a simple voting system, we can rank multiple types of rankings, and then we get a reordered list with the most relevant text being on the top. It's like a Google search, the idea for it. So hopefully our analysts will find the relevant information in the first or second paragraph. So that's what we're using it.
Yeah, to bubble up information. So yeah,
exactly.
Bits.
Yes, yes.
Well, it's pretty cool.
Thank you.
I interrupted you. Sorry.
No, it's okay. Oh, it's okay. It's just you are semantically comparing different types of texts. In essence, that's what we're doing.
All right. Well, those were the questions from the chat. I personally don't have any others. Not sure if Dan wants to know something.
No, not for the presentation, but then I was wondering if you can share. You mentioned you're doing a lot of research and also evolving this sort of solution. So, what would be the next step for you? What is your next challenge?
Well, I'll take this. Mihai and Andrei, they represent the research and development arm of the digital innovation team that all of us are working for. And the mode of that team's work, and I wish I was as smart as they are to be part of that team. And the mode of that team's work is to do the early, like idea level or proof of concept level R&D, almost like in this ConkWorks mode, so to say. So when an idea or the proof of concept reaches a level of maturity that that you can take the courage to let it go and live her own life, that's where our other teams take those ideas and work on their analysis and integration with either our existing environments or creation of standalone environments, so to say. But that lucky team that these gentlemen represent is lucky because they basically work as the in-house applied scientists. It then becomes my job how to give these ideas more life, more maturity, but ideas spend their childhood in that team. So they're lucky they don't need to think about that. They can fully concentrate on the idea in its purest form.
Yeah, that sounds really, really great. You're lucky from that perspective.
Yeah, we second that.
Exactly.
I mean, it's always, if I'm taking one step back, it's always the challenge of when you're starting a new project and you have a clean slate, a blank sheet of paper. But now if you add also sort of this research type of work on top of that, and then you're at the level you're discovering what's possible and what's not and how to combine several technologies, makes it even better.
Yes, I think in our innovation journey, the one lesson we've learned was that innovation happens when its R&D mode is clearly different in its cadence, in its ambience, if you will, than the, I would say, integration or implementation mode. Both modes are critically important and both modes require different types of, I would say, thinking and different types of approaches. We used to do everything together. We learned the lesson hard, I could confess. And now we've split these phases and think, actually go faster.
That was the sound of something going faster, for sure.
I suppose so.
Well, gentlemen, yeah, that being said, thank you very much. Again, I really enjoyed the session. I think both the content, but also the fact that, like I said before, it was, let's say, the fantastic trio, and you, yeah, switched places in the conversation. So it's
the Three Musketeers. So thank you, guys. Thanks. Feel free to contact us anytime. You can reach us out on LinkedIn, mail. You'll have the presentation. So yeah, we're open to help anybody with open source information at least.